Hello all. In this set of lectures, I'm going to talk about sets. Okay. So we'll first look at what a set means and mathematical notation for representing sets. And we will today look at a lot of definitions like subsets, power sets, universal sets, and so on. And then we'll look at things like Cartesian products of sets, right? So today's lecture is going to be lot of theory. So I suggest that you take breaks whenever you feel like tired. Pause the video, take a break, and come back, right? Because it's going to be a lot of definitions. Right. So what is a set? Well, a set is a well-defined collection of objects, right? So this word well-defined is very important here. It has to be well-defined. You have to be able to identify the items in your set without any confusion. For example, I can't, if I say a set of tall students, that's not really a set in the sense of, in a mathematical sense, right? But if I say students who are taller than, say, 5 feet to 6 feet, then that is a proper set because I can identify them and categorize them into that set. Okay. And in a set, you can have a mix of items, right? For example, you might have letters, you might have numbers. As far as you can identify them, right? As far as you can define them, it, it it's a proper set, right? Next thing, it doesn't have any order. The order doesn't matter, right? Say if I say 1 2 3 or 2 3 1 or like any combination of that, still they are the same set, right? Because in that set I have 1 2 3, all these three elements, and the order in which they appear is is irrelevant, right? Now the objects in a set, they are called elements, right? Going back to the example that I used earlier, 1 2 3, these numbers, they are elements of this particular set. Okay, right. So when we want to write a set, we usually use a capital letter to denote a set, right? Say capital A can be a set, capital B can be a set, C, D, and so on, right? So usually we use a capital letter to denote a set. And the elements in the set, we write them within these curly brackets, right? For example, I have a set called A, and in this set, I have 1 2 3 4. These four numbers belong to that set, right? And this is how we write. Furthermore, in a set, you don't have duplicated elements, right? For instance, one can't appear more than once, right? Or two can't appear more than once, right? Inside a set, there's only one instance of an element. You can't have more than one element appearing more than once. Okay, so and when you want to sort of show the elements within a set, if there is such a need, you usually use simple letters, right? And set can have infinite number of elements. For instance, if I just say positive integers, it can go from 1 2 through to infinity, right? So here this set A, in this example, it has infinite number of elements, and so that's one way of writing it. Alternatively, I can just write 1 2 3, and I'm showing the pattern, and at the end put a comma and put three dots, right? So these three dots denote that this goes until infinity, right? So going on to few other notations. Let's say we want to have a set of positive integers below 100, right? So positive integers, you go from 1 to below 100, so 1 up to 99, right? So you can write the entire thing, but that's going to be tedious. So instead what you can do is you can say 1 2 3, put three dots, and then 99. So this says it stops at 99. If you compare these two, in this case I put a comma, three dots, and there's no end, which means this will go until infinity, right? So here three dots, and I'm giving the last value, right? So basically this how you should read this is the same pattern repeats until you come to 99, and then it stops. Okay, Right. Now, let's look at some definitions. And for looking into these definitions, for sort of explaining these definitions, I am going to use these three sets A, B, C. So A has three elements, 1, 2, 3, and B has 1, 2, 3, 4, 5, 6, right? And C has 5, 6, 7, right? So these are the three sets, and I'm going to use these sets to give a few more definitions. Now, the first one is called is element, right? So when we write A, this weird looking E letter, and then the set, that means this element A is in this set capital A, right? So this the way you read it is in, right? So element A is in capital A, right? For example, if I take the previous sets, I can write 1 is in capital A, right? So the element 1, if you look at the set A, 1 is there, right? So you can just write it like that. So this 1, element 1 is in the set A, right? So that is what this weird looking E letter means, right? And obviously you have the not of that as well. So you write a E and you cut it off, and that means the given element is not in the set, right? If you look at it, element 6, number 6 is not in set A, right? So that the fact I can write it like this, right? So there's another symbol uh, that is being used, and this one is called subset, right? So if all elements that are in A are also in B, then I can write A as a subset of B, right? So the symbol that I use is like this, and this open side, right? And the open side points to the sort of the bigger set, right? So if I write it like this, then A is the subset. A has lesser elements, and all the elements that are in A are actually in B as well. Look at this example. A has 1, 2, 3, and B has 1, 2, 3, and more than that as well, right? So all the elements that are there in A, they are in B, right? So that is what this means, right? And obviously you have the not of that as well. So you put the same symbol and you sort of cut it with a line, and that is to say A is not a subset of B. For example, I can write C is not a subset of B because C has 5, 6, 7, and if you look at B, you have 5 and 6, but 7 is not there, right? So it's not a subset. Okay. Right. So let's look at a few more definitions, keeping the same arrays. Now, there's another mark. It's the same thing, but you call this a proper subset. Right. Now, in the earlier case, if you had a close look at it, there is another line underneath, right? So that means it can be a subset and it can also be equal as well, right? For example, A and B might have the same elements. In that case, A is a proper subset of A is a subset of B, right? If A and B has the same elements, it still falls under the same definition, right? All the elements that are there in A are also in B, right? But in this case, if you want to use this symbol, you have to say A, all the elements that are in A are in B, but B should have more elements as well, right? It has to be bigger, right? So to denote that, that little line that you had underneath, you have taken it out, right? So that little line meant it could be equal as well, right? So in this case, it can't be equal. It's a bigger set, right? So you call it a proper subset, right? And then of course you have the not of that as well. So when you write the same sign and when you cut it off, that means it's not a subset, right? It's not a proper subset, right? So the earlier symbol with the line underneath, that's called subset, and the line without this symbol that you have in this particular side, it's called a proper subset. So to be a proper subset, you should have all the elements in the other set and more. To be a subset, you should have all the elements in the other set. That's it, right? You need not have more. Got it? Right. Okay. So before we move on, I wanted to introduce a few very important number sets. So you need to remember these number sets. So the first set of numbers is called natural numbers, right? So these are the numbers that we count from 1, 2, 3, 4, 5, 6, and it goes until infinity, right? So you use this sort of special looking n, right? So when you're writing it on a piece of paper, you just write capital N. But if you are like typing it on a word editor or whatever, then you have this special looking n sign to denote the natural numbers, the set of natural numbers, right? And then you have z that denotes integers, right? So from minus infinity till till plus infinity, all the numbers, all the integers, right? Remember, integers, they don't have fractions, whole numbers. They are called they're denoted by this z, right? So these letters, they are fixed, they are used for this particular notation. Now earlier I was using capital A to denote any set, right? So in one example I said A is this, and then in the next slide I use same letter A for something else, right? But this n, this weird looking n that you see on the slide, that is used to denote the set of natural numbers. This z is used to denote integers, right? And then you can put this z plus to denote the positive side of it, right? So all the positive integers, right? And then there are other two sets. One is called r. They are called real numbers. So right now I'm not going to go into what a real number means. Later on we will look at what real numbers. Obviously you have some other numbers. So real numbers are a simple way of defining it is all the numbers that you know up to now, they are real numbers, right? So there's another class of numbers called complex numbers, which are denoted by a capital C. Uh, so we'll look at them later on. But for now, all the numbers that you know, 1, 1.1, 1.111, all those numbers that are denoted by this capital R, right? And this Q, they denote what are called rational numbers. So later on, I'll try to define what rational numbers are. But remember these ones. N means natural, Z means integers, and R means real numbers, and Q means rational numbers. Rational numbers I'm going to define in a later slide. Okay. Right, so let's look at a few more definitions. Now, two sets are said to be equivalent if they have the same number of elements. Right? Elements themselves can be different, but the number is the same. As an example, a set might have 3 books, and another set, let's say set A has 3 books in it, and set B has 3 tall guys. Right? A and B are equivalent because they have the same number of elements. Right? And then, of course, two sets are said to be equal if they have the same elements and all the elements. Right? So everything that you have in A are in B, and everything that you have in B are in A. In that case, you call them equal. Right? So don't mix these two words up. Equivalent means you have the same number. Elements can be anything. Elements can be different, but the number of elements you have are the same. And then equal means the number of elements are the same, and also the values of these elements are the same, right? And then the singleton set, it's a fancy word of saying it's a set which has only one element, right? So it's kind of a important term. You will find this in software engineering and various other places. It means to say you have only one. Okay. And then you have a empty set. You can have empty set as well, right? And that empty set is denoted by this zero with a, with a dash, sort of slash coming through, or this curly brackets without anything, right? So these denote an empty set, a set where there are no elements, right? So that is called an empty set, and this is how you write an empty set. Okay, so when it comes to specifying sets, people use interesting notation. So it takes a little bit of thinking. So let's go through some examples, and let's try to grasp this idea. Right? For example, let's say I want to define all the students who are taking this course. right? So what I do is I can write it like this. I can say set B is equal to all the students taking this course. So that's like a very sort of a primitive way of doing it. But a more sort of a like a rigorous mathematical way of doing it is, so this in this set B, I have these S's such that, so this line you should read it as such that S is a student following this course, right? So what am I saying? In my set B, I have S's such that the S is doing the course, right? So the student S, if the student S is doing the course, then he is in this set B, right? So that is what this means. Okay, right. So for example, let's say I want to define another set. I want to define uh, natural numbers which are less than 10, right? So I can say x such that x is in this set. Remember this sign, this weird looking sign, it means x has to be in this natural number set, right? So remember the rational number set, but what does it do? It's 1 2 3 4 up to infinity, right? So it has to be one of these. So x uh, a has all the x's such that x is in this, and x has to be, sorry about this mark, it has to be less than 10, right? So I have two conditions. X has to be a natural number, one, and also it has to be less than 10, right? So every x that is satisfying these two conditions are in this set A. That is what this means. So every x, that is what this little x means at the very beginning, right? Such that x is is a natural number and it's below 10, right? So if you expand that set out, you have all the numbers from 1 to 9. Right? So I'm going to use the same notation to define these rational numbers. Right? So a rational number is such that it has to be a real. So a rational number x is such that x has to be a real number. So it's basically all the numbers that you can count, right? 1, uh, 1.1, 1.001, and so on, with all the decimals and all that, such that x is equal to p over q, where p and q are integers, right? So in other words, these rational numbers are real numbers which can be expressed as a division of two integers, right? So if a number is a real number and if it can be written as a division of two integers, then it is called a rational number, right? So if you take 0.5, it's a rational number. Why? 0.5 is 1 divided by 2, right? So p is 1 and q is 2, right? And both are integers, right? And 0.5 is a real number, so 0.5 is a rational number, right? So there are actually irrational numbers which we will talk about later. Some numbers which cannot be written as a division of two integers. For instance, pi, right? So if you remember, when you are calculating the circumference of a circle, you use this pi, right? So pi is such that the value cannot be written as a division of two integers, right? So such numbers we call them irrational, right? So here we are defining the set, the rational numbers, right? So remember this rational number definition as well. It's important for you. Right, so a few other definitions. Again, I'm going to use these three sets, A, B, and C. So the first term that I want to define is called union, right? So the way I remember it, it looks like a U, right? So that's how you write it. A union B means all the elements in both the sets, right? So it's basically you amalgamate the things together. So if you look at in set A, I have 1 2 3, and in B 1 2 3 4 5 6. So I put everything together, and remember, you can't have duplicates, right? So it's basically 1 2 3 4 5 6, and A is not adding anything because all the three elements that are in A are also in B, right? So the union is basically you unite, you put together all the elements in the two sets, right? And then the other one is called the intersection, and that gives you common elements, right? So A intersection B in this example, what are the common elements? 1, 2, 3. Elements 1, 2, and 3, they are in set A, and they are also in set B as well, right? So this is the intersection, right? Now, if two sets, if the intersection is empty, then it is said to be disjoint. If two sets, if their intersection is null, then the two sets are said to be disjoint. Okay. Right. Another definition that I want to do is the universal set. Right. Universal set, usually you denote it with the capital U, and that means all the elements uh, that are there in the set that you draw your set from. Right. So this is a little bit subjective. For example, if I want to, if my set is this -1, 0, 1, and 2, uh, my my universal set would be all the uh, all the integers, right, from -infinity to +infinity, right? Or one might argue this is like the all the real numbers, right? So it's kind of subjective. So it depends on the problem, right? And depending on the problem, you might figure out what the universal set is, right? So universal set is essentially everything in your set, everything in your problem, right? For example, let's say my set A is the number of students in this class, right? Students who are taking this class, and then the universe can be, depending on the problem, might be the students in the university, or it might be the entire population of Sri Lanka, or it might be the entire population of the world, depending on the problem. Okay. Anyway, so the universal set is your universe, everything, right? So this everything obviously depends on what the problem is. Okay. If your problem is just concerned about your university, then your universal set might be just the students in the university, right? If your problem concerns the entire world, then the universal set might be the population of the world. If your set is, the class, the students who are taking this class. Okay. Right, so that's the universal set, and then there's another interesting set called the power set. Now, the power set is written as capital P within brackets A, which means the power set of set A. It gives you all the possible subsets, right? And this is actually this is going to be if I have n elements, I can have 2 to the power n subsets, right? So note that the power set is a set of sets. Right, now, up to now, we were just looking at elements, and in the power set, element is a set by itself, right? Say my array, my set A has 2 elements, 1 and 2, and then the power set, what are the possible subsets, right? Obviously, null, empty set is a possible subset. 1, if I just take this element alone, that's one possible subset. If I take the second element alone, that's another possible subset. And if I take both the elements, that's again another subset, right? So all these subsets put together as a set, that is what we call as the power set. Okay, right. And then the other one, the complement, right? So the complement of a set is basically the elements that does not belong to this set but belongs to the universe, right? For example, if I take my set to be the odd numbers, right, then the complement would be even numbers, right? My universe is all the possible numbers. I have taken out the odd numbers are my set, then the complement of it, what is left, right, that would be the even numbers. Okay, right. And then the last one that I want to talk discuss today is called the Cartesian product of two sets, right? So if I have two sets A and B, let's say A has 1 and 2 and B has 3, 4, and 5, then the Cartesian product of A and B, you write it as A x B. So you put this multiplication mark, B is is actually the ordered pairs of all the elements in A and B, right? So what do I do? If I want to take the Cartesian product of A and B, I take the first element of A and pair it with B, right? So 1 comma 3, right? So that's the first element. Now second time I'm still with the first element of A and I'm going to pair it with the second element of B. So 1 4. Take the first element, pair it with the third. Right, now I'm done. So go back to the second element of A, pair it with the first element of B. So I get 2 and 3. Take the second element, pair it with the second element here, 2 and 4 and 2 and 5. Right, all those put together, that is called the Cartesian product. Okay. Right, so that's all that I have for today. So it's basically a lot of definitions about sets. So what I want you to do is, so these are the topics that I covered. Right? So we try to define what a set is, and we talked about how to represent sets, and we looked at various notations that you are using, like subsets and is in proper subsets and so on, right? And then we looked at different types of sets, power sets, universal sets, Cartesian products, and so on. Right? So these are the topics that we covered, and we will continue with this lecture. We will look at a few other things in the coming lectures as well. And I want you to try out the tutorial that is there uh, in, uh, in the learning management system. Thank you very much.